And I will switch to English. So a preview of the lab today. So this is where we stopped in the last class. So the idea will be that you will generate a messaging system. So essentially you will be able to message each other's machines, each other's computers. So how this will work in general is that we would be in a physical room, if you still remember those days. And the idea would be that you each on your machine implement a client and a server that will interact in a peer-to-peer system. So the first problem that needs to be overcome is somehow how to interact with or how to share each other's details. So the protocol we'll use is based on TCP/IP, the internet basically. So you would need to know each other's IPs and also ports and so forth. So there's the first question of how do you all connect to each other. So we could do something where you passed messages between each other and so forth. But how we implement it here is a central server that I would normally run on my machine, on my notebook. And that I would give the IP to everyone. So if you all know the IP, then you know how to connect to the peer-to-peer system. And then once you have the IPs, you've collected the IPs of the people in the service, then it becomes completely peer-to-peer in the sense that you can message anyone, anyone you like at any time, and it doesn't go through the central server. So the messaging then becomes direct. So this has some advantages and disadvantages. The first thing is that your messages between you, the students, doesn't go through my system. So I have no idea what you're saying to each other, which is good if you maybe want to say bad things about me, for example, and not hurt my feelings. A couple of disadvantages is that if you try to message someone who's currently offline, that message will fail. Essentially, the connection will fail, the message will fail. Whereas if we had a central server that was available all of the time, then we could actually somehow relay the message to the server, and the server could then send it when it detects that somebody else has come online. So there are advantages and disadvantages to the system. So it's somehow a mix between client server and peer-to-peer. So the sort of directory of IPs and so forth that's used is similar to client server. But when you start messaging each other, that's pure peer-to-peer. Okay, so this would be the idea that from your notebook you can send some messages to other people in the class, and they would read it in their code. They would receive the message and print it. Okay, so actually, I've already given the answer to this question. So how do we design a system such that peers can find the IPs of other peers? So again, one option would be we just pass pieces of paper around or something with the IPs, or we email them or use some other communication to manually share the contacts. But in this case, we'll use a central server where everybody registers their details, and they can receive the details of others who have registered there. Such that the peers can send and receive messages to from other peers. Again, we have the two options. The one we use is that the messaging is direct between peers. The other option will be to go through a central server. And each of these options has its advantages and disadvantages, like we discussed. So if you were to implement this in Python, C, Java, how would you do this, right? So if you were to implement this sort of system, so you could start to think about doing things like running web servers on each machine and then having an API that you could call over the web to send a message, take some action and so forth. But essentially that's a whole big infrastructure that you would need just for this. So if you were to implement it in Java or C or Python, the question is there a more native way to do that where you don't have to have this whole, you don't have to implement for example, the entire HTTP protocol and HTML or use some sort of web server that does that. So a much more direct way of doing that is the notion of, I'm going to open the chat here, is the notion of remote procedure calls, or essentially remote method invocation. It's called in Java RMI, which allows you to basically call programs that are running on other machines as if they were running on your machine. So we'll see how that works. So why is Java RMI important? What I'd like to do would be to have this one class to show you how you could build a distributed system yourself from the ground up using Java skills, but you could do the same thing in C, using RPC libraries. You could do something similar in Python, although I don't actually know off the top of my head what it's called in Python. So basically, if you know a bit of Java, then you should be able to implement a system like this that could work in a classroom. Okay, so what is Java RMI? The idea would be that we have a client and we have a server. So the server has Java code implemented, and the client wants to call that Java code on the server. And then that call goes over the network. So essentially, the client can invoke a method running here, a Java class or some Java application running here. It can invoke whatever method it wants. And then the server has to send back the return value of that method. Whatever the method returns, it has to send it over the network. This network here is based on TCP/IP. It's the internet, effectively. So this is called remote method invocation, invoking methods, Java methods on remote machines. So how does this operate? The key concept here is the notion of a stub and a skeleton. So essentially, a stub is the client-side view of an interface of things it can call. I can call put, I can call get, I can call delete, I can call time, I can call, these are the methods. This is the interface I have. I can call these methods. And on the server, we have a skeleton that has that interface and then implements that. It actually says, what does put do on the server side? What does get do? So what happens is the client, the stub on the client will send messages, we can send requests to the skeleton through the stub. So it's essentially an interface that's on the client. It's the view of the interface that the client has. Which then must involve sending, serializing. Since we're going over the network, we have to somehow write the request and the arguments into bits, send them over the network, and then transfer them, right? On the other side, the skeleton will pass the call from the stub. So it receives somehow the call from the stub, and it will pass it on to whatever implements that method on the server. So it'll have to deserialize the arguments, like turn the zeros and ones back into the ints or string arrays or whatever the arguments were, and then pass those to the implementation on the server. So then the skeleton will pass the response back to the stub. Again, over the network, and then again, the stub will deserialize the return value. So if you have a method like put that returns a string, then the skeleton will return the string over the network, and the client will see that as if it were a normal Java method. So I'm not going to get into the code in too much detail. These are more examples that you can review for the lab in particular, but essentially what we have here is an interface. This is just a normal Java interface. Yeah, we just give the method signatures, what arguments they take, what they return, what kinds of exceptions they throw, their visibility, and so forth. So this is an interface. And this is essentially what the client and the server need. They need to agree on an interface. What is the interface that's being shared between both? Right? So we call this interface on the client side a stub, and we call it on the server side a skeleton. It's just the same interface most times, at least the same interface, but we use stub to refer to it on the client, and we use skeleton to refer to it on the server. The server has to implement the skeleton. It means it has to implement the server-side interface. It has to implement the interface, we could say. It should be the same. So here we see a typical implementation. There's really nothing here. We have a class that implements the interface. There's still no RMI-specific things going on here. We just have some implementation of, in this case, a directory server that will map usernames to information about users. You can create users, you can get the full directory, the full map of usernames and users, and you can remove a user according to a certain username if necessary. So this is the actual implementation of the central server. There is one small problem here that a student a long time ago pointed out to me, which is very subtle, and I didn't realize, and I had to change the implementation afterwards, which is the synchronization. So there is this map here. I'm using a hash map, which is not, if you know Java, it's not thread safe. It's not built to be used with multiple threads. So what you would probably need here is something like a concurrent hash map, because you might have multiple clients calling this skeleton implementation. and you could call, you could have multiple, so you could have multiple clients adding and deleting stuff at the same time. So we need either to have something that's thread safe, like a concurrent hash map, or we need to synchronize some of these. We have to have synchronized blocks to avoid, creating some invalid map. Okay, so how does the RMI work? What we've seen so far is pure Java, right? So now we somehow need to do the connection, wire the client to the server. So what happens is the server typically might have several implementations of several interfaces. So the skeleton has a registry, and this registry is just like a dictionary. It's like a map where you can use a key to name some implementation of an interface, and then it will register as a value the implementation of that interface. Okay, so these are sorts of like the options. This is almost like the API of the server. This is like, or it's almost like a meta API, right? It's sort of like you have different APIs, right? So essentially you have a key, which is a string, and then you have an implementation behind that. So this is the code on how you do it. This is our first example of RMI, where we create a registry, which we can do by either specifying the port if we want to run it on localhost, or by specifying the host name as well, which might be, for example, the IP address, or dcc.uchile.cl, or whatever it might be. So this creates a registry. Any questions so far? Okay, so this is like a dictionary on the server side that says, hey, these are all the things I offer. Here's the ID, the string, and here's the actual implementation of this thing. So the only thing we really need to do then is to register the implementation in the registry. So we have to use this weird looking RMI method here, which essentially creates a stub, a remotely callable interface using the implementation that we saw earlier of that interface. So we need this remote object, which is just a remotely invocable interface. We need a name, and then we just add it. We bind it in the registry. We just put it to the registry where we give the name of the implementation and the implementation object itself. And we're good, right? So the server is pretty much ready to go. Of course, you could add several implementations under several keys of different types of interfaces and so forth. Okay, so how about the client? So the client has to connect to the registry of the server. So it needs to know the port and or the host name or the IP of the server, right? This is just to establish the network connection over TCP IP. So it will retrieve the skeleton or the stub with a particular key, right? So it will say, for example, I want the stub, I want the interface for SK2, right? And then it will return that interface. And this will be then a stub on the client. It's just the signatures of the methods, not the implementation. And how this would work. So we have to have a host name, we have to have a port, we have to have a name for the implementation that we want to invoke, the key in the registry for which implementation we want. Then we call this RMI magic-y stuff here, where we very similarly, instead of creating a registry, we're going to get a registry over the network. And then we're going to do a lookup. Instead of binding something or adding something to the registry, we're going to get something from the registry. And that's going to be a stub. Okay, so that will be just the interface that we're going to use on the client. What happens then? The client has this interface, this user directory stub, which is just the method signatures. And you can just use it almost as if it were a local class. So it calls the method, serializes the arguments, the server does the processing, and the server deserializes the result. Right? So here's how it would look once the client has this remote interface, this interface that it can call, the stub. It can just use this as if it were a standard Java object, right? Stub.get directory, stub.create user, stub.get directory, and so forth. So what are we doing here? We get the list of all of the users and their usernames. We print them out. We create a new user. in my case, my details. I want to create that user. So I want to register myself, and that will then be sent to the server. That call will not be executed locally. It will be executed on the server. And if we have lots of clients doing this, then all of the people's details will be registered on the central server. Then if I want to get the details of people I can message, I can do get directory. I can print out all those people, and then I can, for example, remove myself. I can use the stub whatever way the server allows me, whatever the interface is provided. So there are some minor differences between RMI locally. It looks very similar once we have the object set up, but there are some important differences. The first is that remote calls are passed by value. They are not passed by reference, which means that objects are not modified directly. So you could imagine, for example, let's say if you, let's say you get back here we have the user, right? If I were to maybe do user.delete or user.set IP and change the IP, locally on the client, that won't be seen on the server. So that would be your local object. Essentially, there's now two copies of the objects, one on the client and one on the server. And whatever isn't called through the stub won't be coordinated between the client and the server. So it acts a bit more like pass by value, which is maybe not the most accurate sense, but you just have to remember that there are copies on the client and copies on the server, and they don't update each other. The only communication is through the stub. So if you change those objects outside the stub, then it's not going to be coordinated. Everything passed and returned must be serializable. So the key difference, of course, as well, is we have to send everything over the network. So we need to be able to serialize everything. So often if you have your own custom class, all it means is that you just need to implement serializable. And so long as all the things you have in that class are in turn serializable, you should be good to go. Finally, every stub and skeleton must throw a remote exception. It's the only type of exception you can have. So if you have other types of exceptions you want to handle, you'll have to wrap them in a remote exception. And the server implementation can only throw a remote exception. So between the client and the server, you can only be passing remote exceptions effectively.
Professor?
Okay, so that's the introduction to RMI. There is one small last detail to mention, which is that we're not in the same physical class, which probably doesn't come as a surprise too, but how we would normally do this lab is that you from your machine, your notebook, can message other people directly on their notebook, and that's possible because we all have the same router, we have the same, we're in the same room, we're all connected to the same network, and therefore it's relatively easy. In this sort of scenario, it would not work well. It could work in theory, but there's going to be problems with firewalls, there's going to be problems with different sorts of ports being blocked and different connections. So there are a lot of unpredictable factors in terms of getting this to work. So what we're going to do is simulate it a little bit. So we're actually going to be all on the same server using different ports. So each of these will all be on one server in the DCC, and each messaging client will have a different port. So it's a little bit maybe less interesting, but hopefully you'll still get the idea. So Pablo, you have a question?
Yes. What do you mean when you say serialized? It's like,
I'm not sure if you're talking, Pablo, but I cannot hear you. Can other people hear you?
Yeah, we can.
Yeah.
You can. Or at least I see more green boxes. No?
Okay.
You can hear. So it's just me. I cannot hear. I'm going to stop share for a second and see what my speaker is doing. I've had a lot of problems with my audio today. My headphones died, and that was the start of my issues. The speaker is using the microphone, but the microphone doesn't have. Let's try now. Sorry.
Do you hear me?
Yep.
Okay. What do you mean with serialize the data?
Serialized.
It's like a special form, like giving a special format to the objects
Yeah.
before sending them, and then like doing the inverse operation, something like that.
Yep, exactly. Yep, that's pretty much it. So you need, for serialization to work, you need both serialization and deserialization. And what it refers to is for converting a Java object, potentially complex Java object with, lots of different member variables and so forth, but converting that into a sequence of bytes. And then on the other side, being able to process that sequence of bytes on the other side of, for example, the network, or you could also serialize to a disk and deserialize later from the disk. But on the other side, you need to deserialize and then say how to convert those bytes into Java objects. So essentially, it's the mapping from Java objects or whatever programming language you're using, it's objects to bytes. And deserialization is from bytes to those objects again.
Okay, thank you.
Yep. And if you see the word marshalling, it's just an older term, or it's a term that's often used as well. So it's sometimes called marshalling and demarshalling, or serialization and deserialization. If there's a difference between the two, I don't know. I don't know. I don't know what it is, if there's a distinction. More questions or doubts? Okay, so we're going to pass to the Discord, and we're going to give you most of the implementation you need for what we discussed, and there's a few details that you'll need to fill in. So hopefully, Joaquín.
Sí, quería preguntar si ya están disponibles las diapositivas que mostró recién.
Yeah, so they would be in the last class. So this is just the end of class 2. So if you go to Enlaces and go to the webpage, go to the list of slides there, you'll find these slides at the end of that.
Okay, muchas gracias.
And Alberto just published the enunciado. So we'll pass to Discord. When we pass to Discord, I'll give you a couple of minutes in case you haven't formed groups already, and then I'll automatically assign. So I've been working a little bit on the automatic assignment, so hopefully, fingers crossed, it'll work a bit better. I got some guinea pigs from databases to enter a Discord server where I could try to do some testing. So fingers crossed it goes better. So yeah, we'll enter the Discord. You'll have a couple of minutes, but we'll try to assign people as quickly as possible. Within the next 3 or 4 minutes, we'll assign everyone, whoever doesn't have a group. So if you want to form groups as quickly as you can. Otherwise, in 3 or 4 minutes, we'll just assign whoever doesn't have a group randomly to open groups. So I'll leave on the Zoom here, just in case there's any questions. But from now on, we'll talk in Discord. See you there.